Unit 7, Lesson 8, Definition and Properties of Volume. There are two student outcomes as a result of this lesson. The first is that students understand the precise language that describes the properties of volume. Second, students understand that the volume of any right cylinder is given by the formula area of base times height. So in this opening exercise, we're using the following image to answer why is the area formula for a right triangle A equal to 1/2 base times height, where B is the length of the base and H is the height of the triangle. So the right triangle may be rotated about the midpoint of the hypotenuse so that two triangles together form a rectangle. The area of the rectangle is base times height. So since we have two congruent right triangles together that have base times height, then one right triangle is 1/2 that. So it's 1/2 base times height. Here's the answer to the question as to why. Please take this time to pause in order to write down what the answer is. And when they speak of the right triangle being rotated about the midpoint of the hypotenuse, we're talking about this position. Using the following image, why is the volume formula for a triangular prism V is equal to the capital A times H, where A is the area of the base and H is the height of the prism. So A is the area of the base, and we have H as the height of the prism. So the copy of a triangular prism with a right triangle base can be rotated about the axis shown so that the two triangular prisms together form a rectangular prism with a volume 2 times capital A times H, where capital A is the area of the base. So since you have two congruent right triangular prisms together that have a volume described by 2 times capital A times H, the triangular prism has a volume half that value, or just capital A times H. So everything I just stated is written here. Please take a moment to pause this so you can write this down. Please note that these responses incorporates the idea of a rotation in 3 dimensions. Rigid motions behave the same in 3 dimensions as they do in 2 dimensions, which we've already studied. Okay, so keep in mind that these responses incorporate the idea of a rotation in 3 dimensions. Rigid motions behave the same in 3D compared to 2D. I'm skipping over this because we're not able to discuss this. So now imagine a similar situation but in 3 dimensions. So here we have an elliptical cylinder, and we studied area on a grid with lower approximations as well as upper approximations. And I can tell you, let's label this as S, and this is representing a lower approximation. And let's label this as T, and we can see that this is an upper approximation. Okay, so it states here to approximate the volume of this elliptical cylinder, we will use rectangular and triangular prisms to create upper and lower approximations. Okay, we have prisms here, and the reason as to why we're using rectangular and triangular prisms is that we know how to find their volumes. So that's why we're using them. Okay, so I can tell you this. The area of the lower approximation, which I've labeled as S, is less than or equal to the actual area of the elliptical cylinder, so I will label that as B, and that is less than or equal to the area of T, the upper approximation, which makes sense. So we have a nice inequality there. And extending to the third dimension, we would have something that looks like this as well as that. So for volume, we would have to multiply the area of the base to the height. Which is pretty consistent with what we have been doing all along. So let's take a look at some area properties, and please transfer this to your composition notebooks, whether you cut it out and paste it or you just simply copy it by transferring it. And if you do it that way, that'll help you to retain the information also. So area property number 1. The area of a set in 2 dimensions is a number greater than or equal to 0 that measures the size of the set and not the shape. Number 2. The area of a rectangle is given by the formula length times width. The area of a triangle is given by the formula 1/2 base times height. A polygonal region is the union of infinitely many non-overlapping triangular regions and has area the sum of the areas of the triangles. Number 3. Congruent regions have the same area. And number 4, the area of the union of 2 regions is the sum of the areas minus the area of the intersection. So we've already taken a look at these. We're just putting it in a concise way so that it's easier to remember. As far as volume properties are concerned, number 1, the volume of a set in 3 dimensions is a number greater than or equal to 0 that measures the size of the set and not the shape. Number 2, a right rectangular or triangular prism has volume given by the formula area of base times height. A right prism is the union of finitely many non-overlapping right rectangular or triangular prisms and has volume the sum of the volumes of the prisms. Number 3, congruent solids have the same volumes. And number 4, the volume of the union of 2 solids is the sum of the volumes minus the volume of the intersection. So those are the volume properties in a nutshell. Then we have number 5 and 6 for both area and volume. So for area, number 5, the area of the difference of 2 regions where one is contained in the other is the difference of the areas. And number 6, the area of a region A can be estimated by using polygonal regions S and T so that S is contained in A and A is contained in T. Then the area of S is less than or equal to the actual area of the figure, which is less than or equal to the area of T. So this is lower approximation, and this is upper approximation. Number 5 for volume. The volume of the difference of 2 solids where one is contained in the other is the difference of the volumes, as you can see here. And number 6, the volume of V of a solid W can be estimated by using the right prism solids S and T so that we have the inequality, the volume of your lower approximation is less than or equal to the actual volume, which is less than or equal to the upper approximation. So for these exercises, we want to find the volume of the following prisms. So we know that volume is three-dimensional, and we're going to have to find the area of the base, which is 7 times 4, and that's times height of 3. And we get a volume of 84 cubic yards. And for number 2, again, volume is equal to the area of the base times h. So that's 4 times 6 times 1.5. And that gives us 36 cubic centimeters. Please complete the associated homework. Example 1. Find the volume of the pictured circular cylinder to the nearest hundredth. So we know that the volume formula for a circular cylinder is equal to pi r square times h. And we don't have an h here. We do have a diameter of 11 inches. So we're going to have to get a radius of 5.5 inches. That's 1/2 of 11. And we're looking for h. And we have a diameter of 11. We have a right triangle here with a hypotenuse of 14, so we have to use Pythagorean's theorem before we can substitute a good value in for h. So h square, which is the leg, plus 11 square, another leg, is equal to the hypotenuse square. So h is equal to the square root of 14 square minus 11 square, and we get the square root of 75. So h is equal to 8.660. So now the volume is equal to pi times a radius of 5.5 square times a height of 8.660. So we get a total of, which is an approximation of 822.57, because it says round to the hundredth spot, cubic inches. So just keep in mind, especially for a Regents exam, that you may have to find pieces of the information before you can go ahead and substitute it. And always think of Pythagorean's theorem, especially when you're given slanted values. Example 2. A can 12 centimeters tall fits into a rubberized cylindrical holder that is 11.5 centimeters tall, including 1 centimeter for the thickness of the base of the holder. This thickness of the rim of the holder is 1 centimeter. What is the volume of the rubberized material that makes up the holder to the nearest hundredth? So in order to find out what the volume of the rubberized material that makes up the holder, just the holder, is that you're going to have to find the volume of the whole entire figure, which is the can as well as the holder. Then you're going to have to find the volume of the can. And once you do that, you're going to subtract the two and get the volume of just the holder. Okay, so it's the volume of the larger figure, which is the whole, the volume of the can, which is the smaller figure, subtract the two, get just the volume of the holder. So the volume for the whole is pi times a radius of 4.25 square times 11.5. So how did I get 4.25? Well, I know that the diameter of the can right up here is 6.5. Well, this is including 1 centimeters for thickness of the base. So there's going to be, the can probably starts up here. If I was to draw a picture of the can through this holder. So they're talking about the area beneath it, and the thickness of the rim of the holder is 1 centimeters. So that means this expands the entire diameter out 1 centimeter on each side. So the total diameter is 8.5 centimeters. And I needed to take 1/2 of that to get a radius of 4.25. So that's how I got this value here. And I still used the height of just the holder and not the height including the soda, because the soda is above the thickness of the holder. So that's not going to apply. And I get a product of 652.2369. Now, as far as the volume of the can, I'm going to use the same height of 11.5. I'm not going to use the 12 centimeters because it's the volume from here down that I'm worried about. I am going to use the diameter of 6.5, so you take 1/2 of that to get the radius, and we're going to get pi times 3.25 square times 11.5. And that's a product of 381.4119. So we're going to take these two values and subtract them. And what we're left with is 270.82 cubic centimeters as the final output, or the final volume of the rubberized material.